Okay, and we are back again. So now is your turn. Your turn to give this a try. Now, before we get started with that, I just wanted to point out to you on Blackboard, I put a folder up there that calls references. That actually it's in one of the folders for demo files or something like that. It might be under the exercise part or the lecture part. Not sure I remember, but there's a number of files in there that I gave you just for reference. You can get to them in other spots in Blackboard, but just so you have them in one spot, you have your Z table, right? Just like your textbook, except it came from a different textbook. You have the document with the t-test variations. In other words, all the different formulas for everything except the single sample t-test, because that one I thought was simple enough that you didn't need the detailed formulas for it. You have your t-test using a description of how to use SPSS to do t-tests. Okay, you have, I don't remember when, I must have done that a long time ago, 18, probably even before that, who knows, maybe I updated it a little bit. You have basic steps in hypothesis testing, and you have a t-table. You have a table where you can actually look up the t-values, the critical values of t that you need, instead of using Excel if you want to use that. On an exam or on a homework assignment, I will try to make sure that I give you enough tolerance in your answer for it not to make any difference whether you used the table, the T table, the Z table, excuse me, the T table where you should use T table where it's appropriate, right? Or whether you use Excel to find the same number. Excel is going to give you more digits, more significant digits than the tables will, but I'll make sure that you're not disadvantaged. Just a suggestion though, do not round, especially if you're using Excel. You have no reason to round any numbers, because it's doing all the calculating for you. Do not round until your calculations are all done. At the very end, you can go ahead and round, right? And usually round to a reasonable number of significant digits, like 3 significant digits, maybe 4, or something like that, so that so you won't run into trouble with not having over rounded. Yeah, if you round too early, if you do other operations, squaring, square roots, multiplying by things, right? That's going to increase your error if you round a number and then you do other operations. Like if you multiply by 3, you've tripled the error, that you made when you rounded it, right? So you don't want to round until the very end, if at all, right? If for that matter. Okay, so anyway, you have that handy if you need it. Okay, and in fact, I'm going to keep this open in the background here, so in case we need it here. Okay, so if you go into the lab portion of this, there are lab exercises. So we're going to start with this one single sample air samples test. Okay, I'm going to open up Excel, take a quick look at it. And what's happened here is I don't know if you've ever noticed, but if you and you're walking around the city, every once in a while you'll see this weird device that's mounted in a cage. It's got like a little saucer thing on it. It's a air sampling device. It's all kind of packaged up together, and it's inside a cage that's chained to like a light pole or something like that, so people don't steal it, I guess, right? And that is the New York City EPA is required to test the air, the ambient air, to see if we're meeting the National Ambient Air Quality Standard, which is a measure of the amount of carbon monoxide, hydrocarbon particulates, ozone, etc., that's in the air. And if we exceed too many days, we exceed the National Ambient Air Quality Standard for, say, carbon monoxide, well, then the EPA makes a big stink and says you're killing New Yorkers here. You have to do something about it. And the city then makes a lot of noise that we're going to only allow taxi. We're not going to allow private vehicles and anybody else. And they have to pay fare to get in, but that's some things. They make a big stink about it for about maybe, and they're going to put extra tolls and whatever, and limit the times and whatever, and they make a big stink for about maybe a month or so until the national EPA goes away and stops bothering them, and then everything goes back to normal again. Right? So you've seen this happen. Right? You've read the newspapers. So over the last 50 years, how many times have we been through this? So, and you keep hearing about this is going to happen any day now, and it never happens. So at any rate, that's where we stand. So this is an example of this. So right now, these are measuring the level of particulates, hydrocarbon particulates that are in the air, right? And this could be micrograms per cubic meter. It could be a number of different ways. Could actually be particles in some cases, right? But we're going to assume micrograms per cubic meter. And let's say, for argument's sake, that these are not real numbers, of course. Let's say, for argument's sake, that the EPA's limit on the average, it wants to make sure that on the average, New York City is under 50 micrograms per cubic meter, right? So our mean is going to be, our mean particulates is going to be equal to 50. Now, these are the numbers we took, right? So now you want to prove to the EPA that we do not exceed 50 micrograms per cubic meter, right? So we're going to take samples from these different spots in the city. So now the EPA is really interested in what the real measurement is on average for the entire city, not for the 16 locations that we picked here, right? But we can explain to them, well, statistically, we found that we're 95% sure that we're not exceeding in the true mean, we're not exceeding 50 micrograms per cubic meter of air, let's say, right? So we want to make sure we're not exceeding. So we're going to set up a null and alternative hypothesis, and I'm going to set this up for you. So our null hypothesis is that the mean x bar, mean particulates is equal to 0, is equal to 50, and our alternative hypothesis is the mean particulates is not equal to 50. Okay, so how are we going to do that? We want to show with 5% chance of being wrong, 95% certainty, that the mean, whatever x bar here is, right? We're going to calculate x bar, and we're going to calculate the standard deviation. We're going to figure out the number of degrees of freedom. Number of degrees of freedom. We're going to calculate. We're going to look up a T critical for the difference between this average, which you haven't calculated, and the average and the 50 that we're comparing it to, T critical, and we're gonna calculate a T. We're gonna take a T calculator. We're gonna calculate T. Now, in order to do T calculated, right? And in order to do that, we're also going to need the standard error, right? That's going to go on the bottom of that equation. And the equation, just to remind you, is T is equal to x bar minus 50 divided by the standard error. And so now I am going to leave this up to you. I'm going to give you about 5 or 6 minutes. I'm going to leave it up to you to do this calculation in Excel. Okay, so you guys get to work on this right now. You know, by the way, you know where to find this on Blackboard. All these files are in the same place on same folder on Blackboard. So, does anybody want to tell me what your T calculated was? What was T calculated equal to? 2.13. Okay, hang on a second. Let me get this. Enlarge my view. Okay, 2.13. Okay, and what is T critical? What did you look up T critical to be?
My T critical was 2.13. Maybe I flipped it.
Did I flip mine, or I don't know what I did. Did I flip mine too?
I'm sorry, say again.
I'm sorry, I didn't mean to interrupt you earlier. I didn't know if I flipped mine.
I'm sorry. We got 2.13 is T critical. That's what I got from somebody on the chat.
Yeah.
Okay, what do we calculate T to be? The T calculated x bar minus 50 over the standard error.
I got 5.96. Oh, great.
No, go ahead.
It's 0.96 T critical.
Okay, not T critical, T calculated, right? Am I right there? I'm going to calculate it myself now. Okay, so how am I going to calculate that? It's equal to x bar minus 50, right? And what is x bar? X bar, that's going to be equal to, I got to calculate the average first, right? Okay, calculate the average equals the average, parentheses, and I can take the average is all of this, and that's our average, our standard deviation. Those same numbers is going to be this, and our degrees of freedom is going to be 16 minus 1 is going to be 15. Our standard error is going to be equal to my standard deviation divided by the square root of my sample size. My sample size is 16, so that's divided by 4. And now I can calculate what my t-value is. My t-value is going to be equal to, it's going to be equal to x bar minus 50, right, divided by my standard error. Okay, and let me just put parentheses around this so it'll do the calculation properly. And it comes out to be a t-value of calculated t-value of minus 5.47. My average of 36 micrograms per cubic meter are well below the regulation for the EPA. So the likelihood of the true mean for the entire city is way, way less than 0.05. See that? See how big that t-value is? So everybody, yeah, I got somebody else has got about the same, roughly the same error t calculated as I got. Okay, so I could do this in SPSS as well, right? I could compare it to 50 just as we did before. I'm not going to do that right now. I'm going to move on to a second example of this. Okay, I'm going to say don't save this one. Okay, and let's go for independent samples for heart rate. Okay, and as I said before, we are going to assume unequal variances. Let me blow this up a bit. Data, review. Okay, so we're looking at the difference in heart rate between athletes, meaning I think we used this data set before, but athletes who were recruited as athletes for college, and scholar athletes, athletes in the non-varsity group, right? So in other words, these guys play, like in the NCAA, and these guys are just intramural athletes, and we want to see if there's a difference in the heart rates, in the physical fitness or resting heart rates for these two groups. So here is group 1, which is athletes, and here's group 2, which is scholars, right? So we want to know if there's a difference between these two means. These are independent samples, right? So what's our null hypothesis? Our null hypothesis is that mu for athletes is equal to mu for scholars. And our alternative hypothesis is that mu for athletes does not equal mu for scholars. Okay, and so what are we going to find here? We're going to find out the average for both of these. The average heart rate for athletes. This is the average heart rate for scholars. Equals, and for scholars is going to be 2. Okay, and so that's that's the mean. Now what are degrees of, now we're going to assume unequal variances. So if we assume unequal variances, our degrees of freedom is going to be the sum of these two, which is 12 minus 1. So our degrees of freedom is going to be, I'm sorry, it's one group, right, is 6 minus 1, which is only 5. Right, so this is not going to be very easy to prove with this small a sample, right? So it's 5 degrees of freedom that we're going to use for this. Remember, because if you look back at our way, we're going to do this with unequal variances, and we're all going to, from now on, we're going to assume we're not going to assume equal variances. this is going to be our formula for our t-value. This is, bottom part is standard error, and this is our degrees of freedom, but we're going to use one of the two groups minus 1. The smaller of the two groups minus 1. So it gave us 5. Okay, so now I have to figure out what my t-value is going to be. So t, right, is going to be equal to the difference between the two means. That's the top part. This minus this over, and now to figure that out, what am I going to find? I'm going to have to find this the standard deviation 1 squared, standard deviation 2 squared, right? So that's going to be equal to, this is going to be equal to the standard deviation. Do I have standard deviation? I haven't calculated it yet, have I? For each one of these two. For this group, and for this group. So there's my standard deviation of the two groups. So now I have to square my two standard deviations, divide that by my sample size, add the results together, and find the square root. So I am going to wait for you to give me what this standard error is going to be equal to. Right? How am I going to find the standard error? I'm going to take each standard deviation, square it. Then I'm going to divide it by by n minus 1, I think it is. By n, is it n or n minus 1? I forget. By n, right, by 6 on each case. I'm going to add them together. Here we are down here. I'm going to add them together and then take the square root of the whole thing, and that's going to be my standard error. And that's what I'm going to divide into the difference between these two. So anybody want to tell me what the standard error is equal to? I'll wait on somebody to calculate it. Oh, I got some agreement here, 3.39. 3.39 is my standard error. So now what is the difference in heart rate between these two? So the difference in heart rate is equal to 5.16. I'm gonna do it, keep the number positive. I'm gonna do it this way. Doesn't matter, right? It's the magnitude that's important. Divided by my standard error. And I want to make sure it finishes my numerator first before it divides by that. And it comes out to be a really small t-score. That's my t-value, my t calculated, right? I really don't even really have to go any further, right? We know that for a 5 degrees of freedom, that my t critical is going to be very large. It's probably going to be something like 2.2 or 2.3. And we can see that our t value did not exceed the critical value of t. So I failed to reject the null hypothesis. I can do the same thing with SPSS, except this time I'm going to do another little trick in SPSS. I'm going to close this, not save. I'm going to go into SPSS, and I'm going to say open data, and I'm going to navigate to where that file is stored. Okay, I'm going to now go to my desktop first. I'm going to go to session 8. I'm going to go to lab exercises. And where is that file? So here is heart rate. Here's the Excel version of it. Here's the SAV version of it, SPSS version of it. I'm not going to use the SAV version of it. I'm going to use the Excel version of it. Okay, I'm going to use the Excel version of it because I noticed that the data is laid out so that the columns represent my variables. So it's going to be convenient to import it into SPSS. So I'm going to import this Excel file into SPSS. So I'm going to click open. It's going to identify, it's going to realize it's an Excel file. And it's telling me that there is data that it sees between A1 and D13. That D13 is, well, there was some other extraneous stuff at the end here. I don't really need that. I could just actually tell it that I'm really interested in I don't think it'll let me change it here. I can change it in range. I'm not going to bother. I'm just going to delete those once they're imported. And I'm going to say, it looks okay so far. It's checked off, read the variable names from the first row of data. That's why it threw heart rate and sample in there. I'm going to say OK. And it's going to import this data into SPSS. So here's the data imported into SPSS. We have the heart rate. We have the two different groups. Now notice it doesn't know that one represents athletes and two represents scholars. That's because we have to go into the variable view and we have to code it. So one thing I can do right off the bat is I can say, clear this stuff. We don't need that. So I can go into the instead of samples, I can make sure it's labeled athlete type. Okay, and I can tell it one represents athletes and two represents scholar. Say okay, so now we can identify these. So I'm going to go back into my data view and I'm going to say, okay, let's go ahead and run our independent samples t-test. I'm going to go into compare means, independent samples t-test, and I'm going to move heart rate into test variable because that's what our means, it's going to calculate our means. And I'm going to tell them divide them up according to whether they are an athlete or a scholar. And again, I have to define the groups. So I think it was 1 and 2 that they defined as, not 0 and 1, I hope. Okay, click OK, and it runs the t-test for me. Let's see what I get. I get 2 rows here. I get to, noticing the mean, the standard deviation, basically the same as we calculated. I get 2 rows here. Notice that this value is not less than 0.05, so by all rights, I should use the top row. But we're not going to do that. We're only going to work with equal variance is not assumed. It's a more conservative approach, right? Mostly because of the degrees of freedom. So if I look across, if I ignore this and just look to the t-test, my t-value, did I make a mistake in calculation? I must have made a mistake in calculation. We must have had a mistake here somewhere, guys. Did you guys
I
get?
actually had a question. I wanted to go over the t-value.
Okay, I'm going to go back and calculate it again now that I've seen this, right? Actually, I should also check to make sure it's all the same data. I didn't change the data on the way. The numbers could be different here, right? So at any rate, oh no, I just opened the Excel file. This should be exactly the same. Okay, so at any rate, I imported the Excel file. So the t-score is minus 2.164 for 9.5 degrees of freedom. My significance is 0.057. Technically, we don't reject the null hypothesis. It's not less than 0.05, and our t-value does not exceed 2.3, which was the critical value, approximately the critical value of t that we were looking for. So basically, if I was put a gun to your head that says, do I reject or not reject, you would say, don't reject the null hypothesis, fail to reject the null hypothesis, right? However, we can see that this is a relatively significant finding. So if you were the person that did this study, you wouldn't hesitate to publish this information, right? Or to use this information in a useful way. Because I mean, basically you found the same thing that you found what you were looking for. Okay, so let me go back and do this again. Except this time I'm not going to trust you guys. Right? I'm gonna do my own calculation. So let me go back here. Oh, where did I put it? Oh boy, more windows than I know what to do with. I think I closed it. That's okay. I can get it back easy enough. Heart rate. There we go. Again. Okay, so first thing I'm going to do is calculate the means for both of these. Equals the average for athletes and the average for scholars. Okay, that's the means. The means. Now the standard deviation for this group. Standard deviation for this group. This is athletes. Is this. And the standard deviation for this group is this. That's scholars. The sample size for both of them is 6. Sample size is 6. This is standard deviation. This is the sample size. And now I am going to calculate. Okay, so when I want to calculate my t-value, I'm going to find the difference between the top of this is going to be the difference between these two numbers. It's going to be equal to 71 minus 63 is going to be a difference of 7. That's my numerator, difference between x bar 1 and x bar 2. Now my standard error in my denominator, I'm going to have to do a little calculating to get that. First, I'm going to have to take the standard deviation for the first group times itself squared divided by the sample size, which is 6. And that comes out to that. I'm going to do the same thing for the second group. Equals this times itself divided by the sample size, which again is 6. So those are my two standard deviation 1 squared, standard deviation 2 squared. Now that squared and that's just squared and divided by n, So now I'm going to add those two together, equals the sum of those two. Right? I'm going to add them together. So now that's what's on the bottom of that equation, but I got to find its square root. Now that they're both added together, I need the square root of this value. And that's 3.38. So now when I calculate my t-value, my t calculated, and this is going to be equal to 7 divided by what's on the bottom, 3.89, and that comes out to a t-score of 2.16. Okay, does that make sense, you guys? Right? Do you see where I got these numbers from? Those numbers are the square root of S1 squared. It's hard for me to do this here. S1, let me use a caret here or something like that to indicate it. Where is it? S1 squared over n and plus S2 squared over N2 over the two sample sizes, right? And then you're going to add those together and you're going to take the square root. You add those two things together, you add the two of them together, and you take the square root of that whole thing. That's where that bottom came from. Okay, and that is this formula. That's this formula down here. That's what we did there. Are you guys okay with that? Do we see why? Does it matter if it's 7 or minus? No, it doesn't. Because all that tells you is which direction which one is smaller or which one's larger. If I had done it the other way, this would have come out to be -7, right? If I compared the athlete's heartbeat minus scholar's heartbeat, that would have been a -7, and it would have been a t-score of -2.16. If I had done it the other way around, it would have been a positive 2.16. As far as the null hypothesis is concerned and rejecting it, doesn't make a hill of beans worth of difference. We're really just interested in how big a number that is, how big that t calculated is, whether it's positive or negative, and whether it exceeds the critical value of t. Same p-value when you wind up doing it. In fact, if I could show you here, equals, let's see if I can get this work, equals t dot dist dot 2t parentheses, and if I put in the z-score 7, I'm sorry, excuse me. If I put in the z-score 2.16, 2.16, comma, degrees of freedom is what is it here? Oh, you know, it's going to be for us it's going to be different than it was otherwise. We're going to, since we're using we're using 5 for degrees of freedom instead of 9. I'm going to use 5, right? Because since I'm not going to do that big formula that SPSS calculated for degrees of freedom, I'm just going to use 6 minus 1 for 5. That's going to come out to be 0.08. Now, if I made this a negative, right? If this is negative, that value, let's see if the p-value changes. Okay, hang on a second. Equals, it shouldn't change. Negative is equal to this. That's weird. I guess it only takes a positive value. Isn't that weird? Never tried that before. but I guess it wants a positive value for t. But trust me, it doesn't matter. All you're interested in is how far apart are these two means. And that's which one you put in first is irrelevant, right? Because it's the distance between the two means is still the same. Okay, so that's interesting. I never saw. I didn't think that that would be a problem here. ZX, yeah, I guess it only works for a positive number. Actually, I'm kind of surprised at that. X in degrees of freedom minus 1.96. No, doesn't like that number. What do you know? Okay, guess it's got to be a positive number. Okay, I want to do one more thing with you, and that is there is a file on Blackboard. That's our North Carolina birth file. And I'd like you, if you can, to open that file in your version of SPSS. Okay, and if you would, and I am going to open it on here. Let's say open data, navigate to it. And okay, where is it? Where the hell is it? Up here. Session 8. Go into lab exercises. And no, it's not in there. It must be in demo files. Here it is. Okay, I'm going to open it up. Yeah, don't worry about this. This is the formatting on this file is a little is older, right, than the current version of SPSS, but it works fine. I don't have to worry about it. Just say yes. Okay, so here are all the different variables. So I'm going to look at marital status because I only have two values for marital status: married and not married. And I want to compare the weeks of gestation for married women versus unmarried women. So what's our null hypothesis? Our null hypothesis is that the average number of weeks of gestation for married women equals the average number of weeks of gestation for unmarried women. Okay, so we want to test that now using a t-test, comparing two means. We have two samples. We're comparing two means. We want to see if we can reject that null hypothesis. Mean is equal to mean, or mean is not equal to mean. So I'm going to go to analyze. I'm going to go to to compare means. I'm going to go to independent samples t-test. We have two groups here: married women, unmarried women. Even though they're in the same column, we're going to separate it when we actually do the comparison. Compare means, independent samples t-test. So what am I looking at? I'm looking at the completed weeks of gestation. That's a number, it's a numerical variable. Actually, it's showing it as a categorical variable. So, see those things over there? So I'm going to go back in here and I'm going to correct that. Okay, so weeks is not nominal. It's doing that because it sees it's integers. It's a scalar variable. It's an actual measurement. It just happens to be rounded to weeks. Okay, so I'm going to go back in here to my data view. I'm going to go to Analyze, Compare Means, Independent Samples t-test, and I'm going to move in completed weeks of gestation. And in the grouping variable, I am going to put marital status. So now here's the point where it's possible you may see something wonky happen. I think it's 0 and 1. I'm not positive. I think it's 0 and 1. I'm going to give it a try, and I'm going to say OK. See if I identify the groups correctly. So here's my output table, and it didn't produce my table. The independent sample is not produced. There's something wrong. Table is not produced. So I must have gotten that part wrong. So now I'm going to go back to Analyze. Actually, what I really should do is just go back to my variable view and actually look at it and see, let's say, marital status. Oh, the variables are 1 and 2, not 0 and 1. So in case you run into that problem, you know what might be causing it. Analyze, compare means, independent samples t-test. And this time I'm going to change define groups. I'm going to change it to 1 and 2. I'm going to say continue. I'm going to say OK. And let's see what I come up with. First, I get some interesting data back. The sample size for both groups, there were 537 married women, 262 unmarried women. The average The average week of gestation for married women was slightly longer, but is that statistically significant? Okay, it's 38 and three quarters versus 38 and a quarter, about a half a week difference. Here's our standard deviations. They're pretty similar. They're not that far apart. Okay, so let's go down here. And if we assume variance is not equal, our t-value is 2.126. And our degrees of freedom is 363 point so on and so, and our p-value is 0.034. So this tells us we can reject our null hypothesis. And we can say that we can reject the null hypothesis that there's no difference between the mean birth weight, mean weeks of gestation for married women versus unmarried women, right? And we can accept the alternative that there is a difference. Now, the question becomes, remember we were talking about when you have a large sample, like look at the sample size here, right? It's 800 people based at 799 births that are represented here. That's a gigantic sample, right? So we statistically showed that these two numbers are different, but is half a week, is 3 days difference in the average weeks of gestation, is that clinically significant? That's a complete separate question from the finding that they're statistically significantly different, that difference is real, it's not due to chance. Okay, so I think that's enough for tonight. I'm sorry that we didn't get you guys involved to try and do an analysis on screen yourselves. I'll see what I'm going to look. I'll look up and post instructions for the PC and the Mac on what you need to do to make your screen available